Hi, good morning, everyone. As people are streaming in, any questions before we start?
Yes, Professor.
Yeah.
I just wanted to ask about the final project required for CIS 519.
Yeah, we didn't get to it yet, but we're going to announce what's going to happen. It's going to be different than previous years in the sense that we're only going to have a small number of topics that either we will offer or we'll ask you if you have ideas for. And we're going to announce it hopefully Monday or before that.
Thank you.
Any other questions? Okay, so let me start with some again with the administration thing. Again, I want to remind you that the lectures are online. I really would appreciate if people go over it and so that they can be prepared or better prepared for the class. I think it's going to help. Recall that we also have written notes to accompany the lectures, and there's some code that I went over some of it in the class that comes with these written notes. So hopefully this will help you to kind of play with these concepts and get a little bit more fluent in this. Homework 2 available due tomorrow. Quizzes. I left this here just to remind you that some of you are still struggling a little bit with the efficiency of average perceptron or all the averages, and quiz 5 contains a hint for that. So I believe it's question 4, I said. If you understand this and think a little bit about it, this will give you a big hint for the efficiency. Midterm. Midterm is next week on the 28th at the class time. We already put a few midterms, earlier midterms on the website, but this midterm is going to be a little bit different. As I said, it's going to be more shorter questions, quiz-like questions. To the question on the chat, it's going to cover everything, everything that we've covered in class and in the homework, including the last lecture on Monday. And yes, we're recording, so all the recordings are available online. You can access them from the website. They're on YouTube. And any other questions? Okay, so to the other question on chat, yes, that's what we're going to do today. We're going to recap the idea of kernels. We just kind of began to touch upon it. There's a lot more to say. So let me start with this. So that's where we are. I mean, we're dealing with a notion of kernels. And really the picture that you want to have in mind is, or the two pictures are those that I show here on the right. We have some original feature space. In this feature space, the function that we care about, separating the green from the blue, is nonlinear. And all we know how to do is learn linear classifiers because these are efficient, these are easy to use. And the question is, how do we do it? And the solution is enrich the feature space. So as we move from the picture on the top right to the picture on the bottom right, we've enriched the feature space. Instead of working with x1, x2 as the features, we move to x1 square, x2 square. And in this new feature space, the data is linearly separable, everything is easy. Of course, I double the dimensionality of the feature space. In this case, it's only 1 to 2, so 2 to 4, so it doesn't matter. But really, in general, that's going to be a huge blow up, and it's going to be a huge computational blow up. How can we avoid this computational cost of working with this large feature space? And this is where the idea of kernels come in, along with the idea of a dual space. And the key idea of a dual space, which we went over last time and we're going to go over in 3 different ways today, is instead of predicting by computing a dot product of W, the weight vector, with X, we're going to forget about the notion of W. And the prediction is going to be done by computing the dot product of the target X, the blue one in this slide here. I want to compute f of X with other X's that I observed previously. And that's going to be the whole idea. So we're going to show 2 things. One is that we can do this, that this function f of X, which we used to think about as the dot product of W with X, can actually be expressed as some other function of dot product of the target X with other X's. That's one. And 2, that we can do this efficiently. Because so far, the way I've written it here, I didn't do anything. This is still a dot product in a very high dimensional space. We want to be able to show that we can actually compute it by computing dot product in the original space before we blew up the feature space. And that's what we're going to do today. So this is where we started last time. We want to be able to compute this function, dot product of Wx, with a sign on top of it. And I reminded you that we're going to do this in the context of perceptron for now. And this is the update rule for perceptron. Given that, we played with this example, and I'm hoping that by now we all agree that if we start with some W as a weight vector, and we see this sequence of examples, x1, x2, x3, x4, where these are vectors, these are the examples, positive, positive, negative, negative examples. And these are the mistakes that I've made. I've made mistakes only on x1, x2, and x4. Then the resulting weight vector is going to be this. And the real point that I want to make here is that really the weight vector that is a linear sum of the x's, the example I've seen so far. In fact, the example I've made mistakes on so far. And in general, because we can do this, and this is a more general form of what I've done here, where in this case, I'm thinking about the W. I started with W equals 0, and therefore the W at each time can be represented this way, where the alpha I is the number of mistakes I made on xi. This could be 0, which means I don't care about this example because I've never made a mistake on. It's not going to contribute anything to W. But it could be 7, because maybe I went over the data multiple times, and on one of the examples, I made 7 mistakes. So this is where the alpha is. The Y is the label, R is the learning rate. Now, again, the key issue is that we don't care about W, we care about the prediction. So we care about computing this f of X, which I'm showing here on the top right. And if you just plug in W from here into this, that's what you're going to get. You're going to get W transpose dot product X. And with a little bit of algebra, very trivial algebra, this is just a constant, a scalar. I can take it outside the dot product. We get that what we have here is a linear sum of some constants times the dot product of the X I care about, the blue X, with earlier X's. Okay, and this is really what I want you to focus on. So I'm showing that the function, the prediction, can be computed as a function of dot products. And this is the key notion that we're going to move in. This is really what we mean when we say the dual space. So this will allow us to use kernels. And again, I talked about the notion of kernels last time. I'm not going to repeat it. I just want to say that I'm going to present it in 3 different ways. Hopefully, by the 3rd time, everything is going to be simple enough and clear. Okay, so essentially what we are doing is we are transforming the feature space from the original one to an expressive one. In this case, in this example, I'm going to call my set of features T1 up to Tn. These are going to be monomials or conjunctions over the original feature space. And therefore, I'm going to write this dot product as a linear sum over this new feature space that I'm indexing with I. Example, you already know how to compute features. If my feature is x1 and x2 and x4, its value on the example is 1. It's as if I've written here 1. If the feature is x3 and x4, its value on this example, the original example, is 0, and so on. So again, you can think about the previous 2 homeworks, not only the NER, but also what you've done in homework 1, where you took some expressive features and computed them on the examples. That's basically what we're doing here, a transformation from one feature space to another. Okay, so once we buy this notion, we want to talk about how to work with this new representation over the new feature space. Okay. And really the issue that I want to address is I don't want to keep these huge weight vectors, but rather I want to be able to find a more efficient way of doing it. Again, one picture to keep in mind is this one. And so let's go back to what I've shown just 2 minutes ago. We already agreed that if phi of x is the representation of x in the new feature space, computing the dot product with phi of x can be done by computing some function of phi of x, the blue one, with earlier phi of x's. This is just the same thing that I've done before, only that instead of x, I'm calling it now phi of x. This is my new vector. And we will now move to show this in a more explicit way. And here is one way to show it. Up. Okay. Okay. So the example that I'm showing here is what is called polynomial kernel. We're going to reconstruct it a little bit later again, but here is the story that I'm trying to tell here. What I've said so far is that the prediction with respect to a separating hyperplane W can be reproduced or computed instead as a function of dot products of feature-based representation of the examples or some of the examples. So let's assume that I start with I have 2 examples. This example X and dimension, Y is the second example. And I want to map them to a high dimensional space. Which high dimensional space I'm going to choose here? I'm going to choose 2 dimensions. So this is going to be my phi of the vector. It's going to be this vector where I have a constant dimension. I copy the x. This is just x1 up to xn, but I also have all the quadratics and all the mixed term, x1 with x2, x1 with x3, up to xn minus 1 with xn. So that's now, notice I did not add any information, but I'm working now in a quadratic dimension space instead of the original dimension space. So again, you can think about this picture again, right? So in this picture, I wanted to move from x1, x2 to a quadratic feature space. And that's what I'm doing here. This is one way to do it. Now, we care about computing dot product in this space. And we can do it, right? So now that I gave you these two vectors, you know how to compute a dot product between them. Only that if the original space was n-dimensional and computing the dot product would have taken n steps, when I move to the phi space, it's going to take n square steps, order of n square steps. So can I avoid this? Can I avoid taking n square steps? And the answer is yes. I'm going to compute, instead of computing this A product, I'm going to compute B. I'm also going to call it K of XY. And we're going to use this notation a little bit later again. And this is what I'm going to do. I'm going to take the two original vectors, just do a dot product of them. This is an n-step dot product. I'm going to add one, doesn't cost anything. And I'm going to, this is a number, remember, right? So this is now a scalar. I'm going to take the square of this. And my claim is that by computing this B, which is an n-step computation, I get the same result as computing the A, which is an n square step. So the theorem is that A is equal to B. Well, I'm cheating a little bit. And you do it once you try it yourself. Try to compute this dot product. Try to compute this dot product, add the 1 and square, and you'll see that A is almost B. There are some coefficients that appear there. So you'll see that these terms have a square root of 2 coefficient in order to be the same. But really, we don't care about the coefficients because these are going to be the features that we're going to use in learning. And anyhow, we're going to change the weights, right, as we learn. So the coefficients do not matter. So that's the kernel trick. And now, so essentially, the idea is start with some representation of the data, the one that is given to you. In principle, you want to move to this high dimensional space, but don't do it. Instead of explicitly moving to the high dimensional space, do this. And you'll get the same result as if you're working in this higher dimensional space. And so that's one way. We're going to now move to another way of doing the same thing. Question so far? And the answer to the chat, no, it's unrelated to homework 2. Any question?
Yeah, so for phi in the x vector, is it x1 to xn, then x1 squared to xn squared, then x1 times x2 to x? Okay, I think I get it now. Never mind.
So all the linear terms, x1 up to xn, all the quadratic terms, both the pure quadratic terms and the mixed quadratic terms. And also I'm adding a constant 1 here. So this is, if you think about it, if you had n dimensions here, here you will have order of n square. Okay? And again, I suggest to do this exercise. I show it a little bit later in another version of quadratic kernel with an example, but it's a good exercise for you to just do it. Take three-dimensional vectors and just run through this. Okay, so let's now do it in a different way, in a more explicit way. So what is the more explicit way? Let's think again about this W and see what happens to it when we use it in the prediction. And by the way, this is related a little bit to the average perceptron, because understanding this will allow you to implement average perceptron in an easier way. So what am I saying here? That each previous mistake on an example, I'm calling the example Z, makes an additive contribution to some of the coordinates, not to all the coordinates. Why some? Because I'm dealing with a Boolean example, and therefore only when Z is 1, I'm changing the corresponding, when the coordinate of Z is 1, I'm changing the corresponding coordinate of W. And this is exactly what's written here. So, and of course, the value of W then is determined by the number of mistakes and the type of the mistakes. Is it a mistake on a positive example or a negative example? So let's just write this down explicitly. This is where we ended last time. In order to do it, I'm adding this notation. I'm calling P the set of examples on which we promoted the weight. That is the set of examples on which we made mistakes. The set of positive example on which we made mistakes, and D is the set of negative example on which we made mistakes. M is the union of this, which means is the set of all examples on which we made mistakes. And with this notation, I'm claiming that this linear sum or dot product can be written as, I'm keeping this Ti of X here, and this W is basically this vector. Add 1 on all the examples in P for which the coordinate of the vector is 1, subtract 1 on all the examples in D on which the coordinate is 1. And I'm denoting it this way with this additional notation that I'm introducing here. So what is this S? S is 1 if the example was positive and I made a mistake on it. It was -1 if the example was negative and I made a mistake on it. And therefore, this sum here can just be written as Ti of Z time S of Z. So when this is, remember that I'm computing this dot product. So when this guy is 0, it contributes nothing to the dot product. It's not even written here. And when this one is 1, it contributes either 1 or -1 because of the S. That's it. So that's what I have so far. So basically, I've written this f of x in this way, as a sum over all the examples on which I made mistakes of Tiz, Tix. X is the example I care about over the index set. Now, what is written here? This is really a dot product. A dot product between the new representation, the Ti representations of Z. So I'm going to write it this way. This is just writing it again. And the standard notation that I'm going to introduce, again, remember S of Z is just a constant, so I don't need to put it inside this sum. I can take it outside. And I'm denoting K of XZ, the kernel of X and Z, as this, which is really a dot product in the new space. So my prediction is now linear sum over all the examples on which I made a mistake, K of XZ times S of Z. Okay, so far I haven't done anything basically. I just did some algebra and I rewrote the original sum this way. Intuitively, you can think about this as a distance between x and z in the t space, which is always a useful way to think about dot products, right? Dot products actually measure distances, if you want, between two vectors. But again, as I said, all I did is algebra. I still have to compute a sum over a lot of examples, a lot of dimensions, sorry. Why do I do this? The reason we do this algebra is because now that we have this form, we can actually show that we don't need to sum over this huge dimensional space, because k of xz can actually be measured in the original space without explicitly writing this t representation of x and z. This is what is called the kernel trick, and what I'm going to attend to now. Questions so far on this representation? To the question on the chat, how do I know how many dimensions you need to transform to get to a linearly separable result? I don't. And this is actually a very, very good question, because quite often, and I'm going to attend to it at the end of the kernels lecture later today, quite often people overshoot here, and they use a representation that is too expressive, and they pay for it in generalization. But for now, let's assume I do know. And in this case, I actually also overshoot because I used all the features, all the conjunctions possible. Right? I'm using the space of all possible conjunctions, which we already agreed on in the past. There are 3 to the n of these if I start with an x which is n dimension. So my claim, though, is that, again, I don't need to compute it over a dimensionality of 3 to the n, because I can compute it this way. This dot product is actually 2 to the power of same xz, where same xz is the number of features that have the same value for x and z. So just by looking at x and z in the original n-dimensional space, I can determine what is this huge dot product. And let's convince ourselves that that's the case. Okay, this is just rewriting of this and showing you that instead of computing a big dot product, I can compute it in the original space. Let's take the following example. So let's assume that n is 3. This is my x and this is my z. The features are monomials of size 0, which is a constant, 1, 2, and 3, which means I have 3 to the 3, 27 different features, right? But I don't need to compute it. I can just compute the same of x and z. What is same of x and z? The first dimension is the same. The second dimension is not the same. The third dimension is the same. So the same is 2. And the answer is going to be 4. So the dot product is going to be 4. We're going to do 2 things. First of all, we're going to prove this, and I'm going to prove it by example. The formal proof is written here, but we're going to go over this example and convince ourselves. And we'll see another example in the next slide. Okay, so I'm arguing that what I need to do, imagine that you've taken this example X and you've written it in the T space, all 27 monomials. And the same thing you did for Z. You've written all 27 monomials, and then you computed the dot product. What will the value of the dot product be? It will be the value of all those surviving monomials, those that are 1 on both sides, on the x expansion and on the z expansion. So let's think about when will a monomial be the same when you write it in the x space and in the z space. So let's look at this example here in the top right. So my notation here is in red, I'm denoting negation. So this one is not x1 and x3. I'm claiming that not x1 and x3 of 0, 0, 1, which is my x, is the same as not x1 and x3 of 0, 1, 1, which is my z. Both of them are 1. Everyone agrees with that? Again, this is just simple evaluation. Moreover, I'm claiming that if you think about all possible monomials, this guy is the longest monomial for which x and z agree. Why? Because if I'm adding x2 here, on x2 they disagree, right? x1 is 0, x is 0, and z in the second component is 1. So if I was adding the second component, they will not have the same value. Doesn't matter whether I'm adding it in a positive way or in a negative way, they will disagree. So the largest monomial out of size 0, 1, 2, 3, on which x and z can give me the same value is this one, not x1 and x3, because they agree on the first one and the third one. Now that you agree on that, you would also agree that all the subsets of this, they will also agree on them. So what is a subset of this? It could be not x1, I'm showing it here, not x1 of 0, 0, 1 is the same as not x1 of 0, 1, 1. I can take x3, which is another subset. x3 of 0, 0, 1 is the same as x3 of 0, 1, 1. And of course, they agree on the empty monomial. The empty monomial is only 1. So basically, once I found the longest monomial on which they agree, I can take all the subsets of it, and they agree on all of those. And that's it. So they only agree on the longest and the subsets. How many subsets does a set of size 2 has, or a set of size m has? 2 to the m. And therefore, the value of this dot product is going to be 2 to the number of bits that are the same between x and z. Okay, so this takes a little bit of thinking. Hopefully you got this. Here's another example. And you're going to execute this example or the details of this example yourself at home to convince yourself. In this case, I'm going to take a 4-dimensional space. The space of all the features, the new space of features is going to have 3 to the n features. 3 to the 4, 81. Take, for example, 1100 and 1101. And write down the new representation. You don't even have to write all of it because it's very long. It's already 81 dimensions. But once you start writing it down, you'll convince yourself and understand what's happening. So you can completely write it down or just think about how do I compute the dot product in this new feature space? I of x dot product with I of z. And once you do this, convince yourself that this dot product is exactly as 2 to the same xz. What is the same xz here? They agree on the first coordinate, they agree on the second coordinate, they agree on the third coordinate, they disagree on the fourth coordinate. So it's 3, 2 to the 3 is 8. That's it. So once you do this exercise, you will convince yourself that instead of working in an 81-dimensional space, which is tedious, and computing this dot product there, you can actually compute it just by looking at the 4-dimensional vectors. And you can give yourself another exercise where instead of looking at all possible 3 to the n conjunctions, just look at conjunctions up to size 3. Right? There's a lot less of these. This is more related to what you've done in the NER example, where you consider just small conjunctions over the original feature space. It's still a very large feature space, but not as large as the 3 to the n. Question so far? What is Z? Z is this example, 1101. Was there another question inside this question? Or it was just this?
Professor, can you explain again why when the x is not in one dimension, if the x is not equal to z, then we can ignore that.
So let's look at this example again in the top right here. Okay, so I have these two examples, 001 and 011. And I have a lot of features over them. One of the features over them is the second dimension. I'm going to call it the x2 feature. Right? This is a feature. Now, what is the feature? What is the second dimension of 001? It's 0.
Yes.
The second dimension of 0 and 1 is 1.
Yes.
And when you write down the new feature representation of 001, just a second, we lost this. When you write down the 27-dimensional representation of 001, the feature that corresponds to the second dimension is going to align with the feature that corresponds to the second dimension here, but they will not be the same. One of them is going to be 0 here, and the other one is going to be 1, and therefore they will not contribute to the dot product. Because dot product gets a contribution over only if in both vectors it's 1 at the same time, in the same location.
So if when they both are 0,
so what is a dot product? What is a dot product? This is the dot product here.
Yeah.
Right, so you go to the first dimension with the first dimension, the second dimension with the second dimension, third dimension with the third dimension. If in one of the dimensions Ti of z is 0, it does not contribute to the sum. If in one of the dimension Ti of x is 0, it does not contribute to the sum. The only time this contributes to the dot product is for the same I, both Ti of z and Ti of x is 1. Right?
Yes. Yes.
And therefore, the only features that will contribute are those where the evaluation of the feature on 001 and the evaluation of the feature on 011 are going to be 1. And I'm claiming that the only time this is going to happen is when the feature is this, not x1 and x3. You agree that on both these vectors, not x1 and x3 is going to give me 1?
Mm-hmm.
And what I'm saying is that if something else appears in the feature, for example, if x2 appears in the feature, it will never be a match here. One of them is always going to be 0 because they disagree on the second component. So whenever you put into the feature the second component, the value here is going to be, in one of them, the value is going to be 0. So what I suggest you to do is write down a few other conjunctions, a few other features of size 1, 2, 3, or 0, 1, 2, 3, and compute them for 0, 0, 1 and 0, 1, 1, and then convince yourself that this is the longest feature for which both of them will get 1.
Okay. Okay, thanks.
And do this again for the 4-dimensional case. Okay, so what have we done so far? We basically ran an algorithm that is called the dual perceptron algorithm. Let me summarize what we've done. We simply ran perceptron in an online mode, but instead of updating W, we just kept track of the set M, which we define to be the set of all examples on which we made mistakes. Basically, keeping track of the set M allows us to keep track of S of Z, which is written here. We just need to write down whether it was a mistake on a positive example or a negative example. So what we've done is, rather than remembering the weight vector, we remember examples. That's what it means to work in the dual space. Forget weight vectors, just keep track of examples. And with this, we can compute the dual representation or make prediction using the dual representation. So that's a new algorithm, if you want. It produces exactly the same result, but it's not touching a W. Instead, it's only maintaining all the examples and keeping track of whether we made a mistake on them or not. Okay, so I'm going back to the example that I showed before. We've seen it before. Now that you've seen another example, might be easier. I'm not going to go into the details unless there is a question here. Again, the key issue is my data is given to me originally as these examples, original n-dimensional examples. I don't want to work in this space. I want to work in a higher dimensional space. For example, I want to work in this dimensional space, but that's going to take me time because I'll have to compute dot product in this n² dimensional space. Instead, a trick. Now notice that for every kernel definition, the trick is different. Before, the trick was compute same of x, y. Now the trick is compute this dot product, add 1, and then square. Every kernel comes with its own expression of the trick, but in all cases, it's the same, it's a trick. So now you can ask yourself, okay, so how do I do this? I mean, it seems like magic. And indeed, there is some magic here. But let me summarize it before we kind of explain how general this trick is. The summary is, we want to work with degree 2 polynomial features, phi of x. And in this case, the dot product will be in a space of dimensionality order of n². The kernel trick allows you to save and compute the dot product in the n-dimensional space. So, okay, so can you use any k that you want? And the answer is not exactly. You can always use k. The trick is valid if it corresponds to a dot product. You'll see it sometimes as inner product in some dimensional space. Could be even infinite dimensional space, but some features, some dimensional space. For example, you can define k to be this dot product, k of xz, 2 vectors. I didn't even say which dimensional space x and z are, doesn't matter now. I'm defining k as a dot product of x and z square. It's another quadratic kernel. It's a little bit different than the one before, because before I added 1 to this. But still it's quadratic. Let's compute it. So here is an example. So I'm taking X and Z to be two-dimensional spaces because it's easier. So X is X1, X2, Z is Z1, Z2. What am I doing here? This is the dot product between X and Z, right? I'm taking square of it. When I'm taking square of this dot product, I'm getting X1 square, Z1 square, plus on the other side, X2 square, Z2 square, plus 2 times the mixed term. I'm rewriting this now. How do I rewrite it? This way. I'm claiming that this can be written as X1 square, comma. So I'm writing this as a dot product of two three-dimensional vectors. Here is one of them, X1 square, square root of 2x1, x2, x2 square, dot product with the same thing with Z. Z1 square, square root of 2, Z1, Z2, Z2 square. Now let's imagine this. And I want you to be convinced that the dot product of these two vectors is this. You see, you get the x1 square, z1 square from here. You get the x2 square, z2 square from here. And you get the mixed from here. Just a dot product, right? So you take this times this, this times this, this times this. And you see that you got this sum. Everyone is convinced? What did I do here? I did the reverse engineering of what I showed you before, right? So I showed you that this k of xz, which is an operation in the original dimensional space, can also be written as a dot product in a three-dimensional, in a new dimensional space, larger dimensional space. So here, let's say it was two-dimensional space. Here it's three-dimensional space. Okay, so these are the A and B's that I showed before. So in doing that, I also proved to you that this is a kernel. This is exactly the example that we showed before, right? So we kind of prove that K is a valid kernel by explicitly showing that this corresponds to a dot product, right? So I defined a function of X and Z, and I showed that it's a dot product in another dimensional space. Question on this? Okay, so this is the third way we showed the kernel. Okay, so the next comment is something that most of you don't care about. I mean, I showed this explicitly, right? You said, I think that I want to use this as a kernel because I care about this example. Is this a kernel? And I showed you, yes, it's a kernel because I can write it as a dot product. Now, in general, it's not necessarily the case that you have to do this explicitly because there are some general conditions on kernel matrices that have to do with some linear algebra, showing that something is a positive semi-definite matrix and so on. We don't care about it, but unless you do care about it. So, okay, let's give some other examples. You can have a linear kernel. This is just the dot product of X and Z. Of course, it's a kernel because it's just a dot product. You can have a polynomial kernel of degree D, which is dot product of the original space vectors to the power of D. The example I showed you is with D equal 2. You can have polynomial kernel of up to degree D, which is dot product of xz plus some constant. This can be 1 to the power of D. The difference between these two is that if you just take this one, you only get quadratic or D terms. Look at this example before. Right, so this is the example that of d equal 2. All the terms that I get here are degree 2. On the other hand, if you were adding 1 here, as in the previous examples I showed, and also in this example, if you compute this, you will see that you get also mixed degree terms. Also, oh, what's happening? Okay. You will get also terms of degree 1, 2, 3, up to D. Again, this is another example of a kernel. And there are many, many examples of kernels, and in fact, there are rules for how can we construct new kernels from existing ones. And I want to go over some of the rules. And in all cases, you can actually, once you understand the definition of a kernel, which is something, a function over the original vectors that can be written as a dot product in some space, that's the definition, you can prove to yourself that all these are ways to construct new kernels. For example, if you know that K is a kernel, multiplying it by a constant and defining K prime of X prime to be C times K is also a kernel. How would you show, how do you convince yourself? You will write this as phi of X dot product with phi of X prime. And then you will write this as square root of C phi of X dot product with square root of C phi of X prime. And you'll put the square root of C into the vector. So now you show again that this is a dot product. And the same thing would work with each one of these. I'm not going to give the details. I'm just going to list for you some possible operators. So if you take a kernel and multiply by any function f on both sides, so from the original kernel k of x prime, you multiply it by f of x on the left and f of x prime, you get a new kernel. If you apply a polynomial with non-negative coefficients to a kernel, you get a new kernel, right? So if this is a polynomial over z, sum of ai zi, if k is a kernel, p of k is also a kernel. And you can also exponentiate a kernel, and you get a new kernel, e to the power of a kernel. And quite a few other things that you can do, right? So you can add kernels, you can multiply kernels, and you can change the representation of vectors. So you move from x to phi of x, and then you apply the k to the phi of x's. It's also a kernel. So basically, this is a very important operation, but what I want to get to is one of the most important kernels, which is called the Gaussian kernel. Sometimes it's called a radial basis function kernel. The way this function kernel is defined this way, so xz are again vectors in our original space. K of xz is going to be e to the minus x minus z square divided by some constant c. What this is going to give you is a very interesting function of x and z that behaves like this function that I show here, right? So what is this? This is just the square of the Euclidean distance between x and z. C is a constant. You can think sometimes it's going to be computed by some as a function of the distribution of the data, but doesn't have to be. But the important thing to see here is that if you use as C something very, very small, then this fraction here is going to be very, very large. E to the minus is going to be basically 0. So essentially, each item, each x is going to be by itself. If C is very, very large, you're going to get a unique value for all of this, because this is going to be essentially e to the minus 0. So it's 1. So that's one important thing to think about. But even more important is to think about what happens to k of xz when x and z are very close. So what happens when they are very close? This is 0 here. So what you get is e to the minus 0, which is 1. So basically, if you compute the kernel of x with z's that are very close to it, you get 1. It's the peak here. If you compute the kernel of x with z's that are very far from it, you're going to get something close to 0. And that's why you get this peak. So essentially, this Gaussian kernel allows us to smooth around x. Right? So basically, instead of representing x, you're going to represent things that are very close to x, just like x, and things that are very far from x are going to disappear. And again, this is a useful kernel that allows you to, in some sense, take a discrete space and make it a little bit more continuous. It gives a notion of similarity between the examples. You can ask, how do you know that this is a kernel? And it's actually, if you believe the operators that I gave you before, it's very easy to show that this is a kernel just by using them multiple times. So this is the definition of the kernel. And I'm just doing some algebra here. So I'm computing this x minus e squared, it's written here, divided by some constant. I'm pushing the constant inside for all these three. E to the e to this sum is the product of e to this times e to this times e to this. This is just simple algebra. And what I got here is now a function. I'm calling this f of x. The same function on the other side, it's f of z. And in the middle, you got e to the dot product between x and z divided by some constant. Now we know that if the something in the middle is a kernel, this is also a kernel. So I care only about showing that this is a kernel. And this is why is this a kernel? It's a kernel because a dot product is just a kernel. A dot product, a kernel divided by a constant is still a kernel. And exponentiating a kernel is a kernel. So these are three of the operators that I showed. So basically, what I showed now is that this important function, Gaussian kernel, is indeed a kernel because it's a function with this dot product between x and z. So this is a different kernel than the other kernels we talked about because it's really a kernel in a continuous, infinite dimensional space. We cannot directly show, as we showed with the dot products before, the quadratic or the 3 to the n space, how to construct it originally. You have to basically show that it's a kernel this way using the operators. Okay, so summary, what have we done? We basically showed that there is a way to run perceptron. And in fact, exactly the same thing is going to happen with other algorithms. Run it on a very large feature space without actually incurring the cost of keeping a very large weight vector. We do this by computing the analogous to the weight vector directly in the original feature space. And again, the best example for you to think about is this picture of the quadratic, the ellipses that I showed, where we moved from a nonlinear space to a linear space by applying this quadratic kernel. Now, it's important to realize that this is only about efficiency. Sometimes in the literature, this is not explained well, and people give you the idea that working with kernels is actually going to produce better results. Not true. It's exactly the same classifier, only that you are doing it in a more efficient way. Generalization is still relative to the real dimensionality or related properties of the real dimensionality. Okay, and again, kernel became popular because of the use of support vector machines, but they apply for many, many models. As I showed, it applies to perceptron and many other models that we're not going to talk about. We are going to revisit it in about 2 weeks when we talk about support vector machines and show the use of kernels there. Okay. So one, or in fact, before that, question so far? Okay. So should we use kernels? So that's one key question here. Is it always worthwhile to define kernels and work in the dual space? Because you can see that the alternative is either just stay in the original space and hope that everything is linear, or explicitly blow up the feature space, but still run the perceptron as is, compute the long dot products, right? Which is what you're doing in homework 2 when you blew up the feature space in the NER case. You computed some conjunctive features, but you did not use any kernels. You just ran the algorithms over the new feature space. So when do we know whether it's worthwhile to use kernels and work in the dual space and when it's not? So let's do some back on the envelope computation to get some intuition for this. So here's my notation. Let M be the number of examples that we have, and T1, T2 be the dimensionalities that we have. So T2 is the dimensionality in the dual space, and T2 is the dimensionality in primal space, which is the original space, just a fancy name for the original feature space. This is what you will sometimes see in the literature. Okay, so because these are the dimensions, you can think about them as the cost of the dot product, right? In the original space, you're going to pay T2 for each dot product. And in the dual space, you're going to pay T1 for each dot product, right? It's basically the cost of dot product is the cost of the dimensionality. Okay, so what is the cost of running the perceptron? In the primal space, it's T2 times M, right? So essentially, what are you going to do in order to get your prediction, your W? You're going to do M dot product, right? With all the example, you're going to go over each examples, update the W, and you're done. So order of M times T2. What's going to happen in the dual space? How do we make predictions in the dual space? For every example, we are going to compute dot product with all the previous examples. We don't keep a W. We are thinking about if you are in the 7th example, in order to predict on it, you're going to consider first, second, third, up to 6 examples, compute the dot product with them, sum them, and now you have your prediction on the 7th example. And when you get to the 8th example, you're going to compute the dot product with all the previous examples. So as opposed to W that you maintain here you maintain just the set of examples. And that's why you get M squared, right? Because you have M examples, and each one of them, you're going to do a dot product with all the other examples. Well, in fact, all those that are before it. But still, the order of magnitude is all examples, each example with all the other examples. So you have M squared dot products, and each dot product is going to cost you T1 because the dimensionality is T1. Okay? Now, so this is the computational cost. Now, we assume that T1 is much, much smaller than T2. Otherwise, why are we doing all this, right? So this is the original dimensionality, and this is the blow up dimensionality, right? This could be the 3 to the n, or it could be just n squared if this is n, depending on the kernel you choose. But we assume that T1 is smaller than T2. So you can see that comparing T1 M squared and T2 M boils down to the number of examples that you have. Sometimes T1 M squared is going to be smaller than T2M, and sometimes going to be larger depending on M. So the rule of thumb is, if you have a lot of examples, M squared is going to grow much, much faster than M. Don't go to the dual space, stay here. If you have high dimensionality, right, so T2 is becoming very, very large, but M is not so large, then M squared is a cost that you may be willing to pay, and you use the dual space. So that's kind of a rule of thumb. So now in applications today, quite often people use dual space when they use support vector machines. But more often than not, people actually don't do it. They use explicit kernels, kind of like what you did in homework 2 when you computed small conjunctions. You just blow up the feature space, and you're willing to pay for the long dot products. Questions? Okay, so a question here is, what is considered large M? That's a very good question, and there's no good answer here. It really depends on your applications. As you can see, in many natural language text applications, the dimensionality is going to be a function of the vocabulary, which means it's tens of thousands, hundreds of thousands, even millions. And when you do text classifications or any other text-based things, the vocabulary is going to dominate the dimensionality, and it's going to be large. In other applications, maybe medical applications where the features are tests, you can have just a very small number. And in this case, you know, M squared is also going to be very small, and you can do this. So really, it varies on the domain in which you're working. Any other questions? Okay, so as I said, kernels only help us to be more efficient. It doesn't help us in generalization. And going back to a question that was asked on the chat earlier, how do I know how expressive I should be? How much blow up to the feature space should I make? And the answer is we don't know. In fact, you can try. You can try to use quadratic kernels. or quadratic terms, see if it works. If you're expressive enough on the training data, you should get very, very good performance, as you know already. If you're not expressive enough and you don't see good performance on training data, maybe you want to increase your expressivity. The issue with irresponsible use of kernels is that sometimes people say, you know, I don't care, I'm going to add a lot of features, I'm going to use expressive kernels, and then you pay for it in generalization because you're effectively working in a very, very high dimensional space. Your hypothesis space is much, much larger because you're dealing with functions over higher dimensions and you're suffering in generalization. So you basically are overfitting. So there is always a trade-off here between how much do we want to grow the expressivity. And in fact, this is a very good segue to what I want to get to next time. And before that, let me just summarize what we've done on kernels. Really, the use of kernels to learn in the dual space is a very, very important idea. Different kernels may expand or restrict the hypothesis space in useful ways and support learnability. But we have to understand that there are some benefits, but they come with some hazards of when not to use kernels and when to be careful on not blowing up the expressivity too much. Now, the field of kernels is much, much broader than what I've shown here. There's a lot of kernels that people devise in order to deal with structures. For example, if you care about parse trees, you can devise kernels over parse trees. If you care about graphs and you want to classify graphs, you can devise kernels over graphs, and so on and so forth. So there's a lot of literature on dealing with kernels and inventing kernels as functions of simpler kernels in order to, in an easy way, increase the expressivity of your classifier. So I'm not going to touch this. Instead, I'm going to talk a little bit about generalization and give a hint for where are we going to start next time, which directly links to what I just finished with. So really what we want to do is we want to understand when machine learning works. So we talked a lot about algorithms, models, but we don't know when they're going to work. So that's what I want to get to next time. And really, we're going to get a glimpse into theory of generalization. And the basic result that I want to discuss, probably it's going to take a week, is something like this. The error of a function, the error of a predictor that we learn, of course, on a sample from the distribution, right? We're assuming that we get a sample of examples and we want to know how well are we going to do? What's going to be the error? We're going to show that it's actually going to be bounded by the training error that we can, of course, measure, plus some complexity term. And everything in learnability now boils down to, okay, so what is this complexity term? How far is the error that we're going to see in the real world is from what we see on the training? And what we're going to show is that this complexity term is a function of a well-defined functions of the size of the hypothesis space, the number of examples that we see, and how good we want to be. That is, you know, some complexity parameters. So basically, there are some key assumptions and key conditions that we'll have to deal with in order to show that this is so, that the error, the true error, is actually potentially not too far from the training error as a function of these complexity terms. One key condition is going to be that the training data is sampled from the same distribution as the test data. This is called the IID condition, where IID is independently identically distributed examples. And of course, the key question is going to be, how do we estimate this complexity term? As an example, we're going to show one case of a complexity term that looks like this. So the true error on the distribution is going to be bounded by the training error plus this complexity term. And when you read this, hopefully you see that everything makes sense, right? So these complexity terms become smaller as m, the number of examples, goes up. If you see more examples, of course, the training error is going to be closer to the true error. And it grows with the size of the hypothesis space. If there's a lot of hypotheses to choose from, then maybe the training error is not so representative of the true error, because like in decision trees, there's so many trees out there, you can always choose one that minimizes the training error, but says nothing about what's going to happen in the future, as you know from homework 1. So the hypothesis space size is going to be crucial in understanding how far is what we see in the training from what we're going to see in the real world. So that's actually what we're going to discuss next time. And of course, you're going to ask the question of, in this case, it's the size of H, but what happens if H is finite, is not finite? Size of H then is meaningless. We have to come up with some other complexity parameter to determine how far is what we're going to see in the real world is from what we see in training. And that's what we're going to start dealing with next time. Questions before we're done? The midterm covers everything, including some of the ideas that we're going to discuss on Monday. Any other question? Now we're going to repeat the ideas that I talked about today also in the recitations. Come to the office hours and ask questions in the office hours recitation and also in the next lecture. The midterm is open note. You're going to do it at home during the lecture of Wednesday. And yes, we do have a quiz this week. Okay, so for the next question, I will not, I answered this at the beginning of the class. This class and last class. I talked about the format of the midterm, so answer was there. Any other questions? Okay, so I'm going to talk about the midterm again at the beginning of the class on Monday. And please come prepared also with questions. Okay, other than that, have a good rest of the week. Thanks. Okay, the quizzes and answers are available already from the web page. I'm going to verify this, but I think it's already out there. Everyone that solved the quiz can see the answers, by the way. Okay, thank you. And we'll see you Monday.